Welcome back. Today we're going to explore one of the most mind-bending questions in all of physics. What would we actually see if we could approach the speed of light? Not just in theory, not just in equations, but what would our eyes perceive? What would the universe look like? To answer this question, we need to embark on an extraordinary journey. Imagine yourself aboard a spacecraft, one with capabilities far beyond anything we've built today. This vessel has engines powerful enough to accelerate continuously, pushing us faster and faster, bringing us closer and closer to that cosmic speed limit that Einstein told us about over a century ago. Our ship sits on the launch pad, motionless against the backdrop of Earth. The engines ignite. We begin to accelerate away from our home planet, and as we do, we're going to witness phenomena that challenge everything our everyday experience tells us about how the universe works. We'll see light behave in strange ways, watch the fabric of space itself appear to warp and compress, and encounter effects that blur the line between optical illusion and physical reality. But before we dive into the bizarre visuals awaiting us at relativistic speeds, we need to address something fundamental. As our spacecraft picks up velocity, moving faster and faster away from Earth, you might wonder, won't this speed become unbearable? Won't we be pressed back into our seats with crushing force as we approach a significant fraction of light speed? The answer might surprise you. Speed itself has absolutely no effect on the human body. Think about it this way. Right now, as you read these words, you're sitting on Earth, which is rotating at roughly 1,000 miles per hour at the equator. Simultaneously, Earth is orbiting the Sun at about 67,000 miles per hour, and our entire solar system is racing around the galactic center at something like 500,000 miles per hour. Yet you feel none of this motion. Why? Because motion is relative. When you're moving at a constant velocity, there's no physical sensation associated with that movement. Consider what happens when you're on a smooth-running train. If you close your eyes, can you tell whether your train is the one moving or whether you're stationary and another train is passing by? No. The sensation of motion only occurs during acceleration or deceleration, when your velocity is changing. Inside our spacecraft, the same principle applies. We don't feel our speed. We only feel the acceleration, the push from the engines that's changing our velocity. As long as the thrust from our reactors remains at a comfortable level, say equivalent to Earth's gravity or perhaps a bit more, the journey will be perfectly tolerable regardless of how fast we're actually going. Even as our velocity climbs to 90% of light speed, 99%, or even 99.9%, the sensation inside the ship will be no different than it was when we first started accelerating. There is, however, one very real danger associated with traveling at extremely high speeds: collisions. At velocities approaching the speed of light, even the tiniest particle becomes a devastating projectile. A speck of dust, a stray atom, hitting our ship at near light speed would release energy comparable to a nuclear explosion. The kinetic energy of an object increases dramatically with velocity, and at relativistic speeds, even insignificant masses carry tremendous destructive potential. Fortunately, our hypothetical spacecraft is equipped with advanced shielding technology, perhaps an electromagnetic deflector field that pushes charged particles out of our path, or some other mechanism that allows us to navigate through the interstellar medium without being vaporized by cosmic dust. With this protection in place, we're free to accelerate without fear, pushing our velocity higher and higher. Now, as we begin our acceleration away from Earth, the first optical effects start to become apparent. Look through the forward viewport of our ship. The stars ahead of us, the ones in the direction we're traveling, begin to behave strangely. They seem to shift from their normal positions, gradually moving toward the center of our field of view. The constellation patterns you might recognize start to distort. Stars that were spread across a wide angle of sky begin to cluster together, as if the entire forward view is being compressed, contracted toward a point directly ahead. This effect has a perfect analog in everyday life, one you've probably experienced countless times without realizing it. Imagine you're in a car, driving down the highway on a rainy day. The rain is falling vertically, straight down from the clouds above. But what do you see on your windshield? The raindrops don't streak straight down. Instead, they hit the windshield at an angle, coming from ahead of you, as if the rain were falling diagonally. The faster you drive, the more pronounced this effect becomes. Drive fast enough, and the rain appears to be coming almost horizontally straight at your windshield, even though it's actually falling vertically. This happens because you're moving forward through the falling rain. Your forward motion combines with the vertical fall of the raindrops to create an apparent trajectory that's tilted toward you. Light from the stars works exactly the same way. The light rays are traveling through space in a particular direction, but because we're moving, we intercept those rays at a different angle than we would if we were stationary. Just as the rain appears to come from ahead when you're driving, the starlight appears to come from ahead when you're traveling at high speed through space. This phenomenon is called the aberration of light, and it was actually first discovered not by spacecraft traveling at relativistic speeds, but by astronomers observing stars from Earth. Our planet's motion around the sun causes a tiny aberration effect, shifting the apparent positions of stars by a small amount over the course of a year. But on our spacecraft, accelerating to far higher velocities, the effect becomes dramatic. As our speed increases, the aberration grows more extreme. Stars continue to migrate toward the forward direction. The sky ahead of us compresses further and further. Meanwhile, look behind you, back toward Earth, and the stars in that direction. They're doing the opposite. The rearward view is expanding, stretching out. Stars that were clustered together now spread apart, and the density of stars in the aft view decreases. But it's not just the positions of the stars that change. Their brightness changes too. As we accelerate forward, we're catching up to the light waves coming from stars ahead of us. We're intercepting more light per second than we would if we were stationary. The result? The stars in front become brighter. Their intensity increases as more and more light gets funneled into our forward view, concentrated by the aberration effect. Behind us, the opposite occurs. We're outrunning the light from stars in the rear. Fewer photons per second reach us from those stars. The sky behind our spacecraft grows dimmer and dimmer, fading toward darkness as we leave more and more of the starlight behind. This creates an increasingly dramatic contrast. A bright concentration of light ahead, a darkening void behind. The universe begins to take on a searchlight quality, with all illumination focused in the direction of our travel. The aberration of light leads to another bizarre visual effect, one that's perhaps even stranger than the shifting star positions. To understand it, imagine that space itself has a visible structure. Perhaps we're traveling through a region filled with a vast three-dimensional grid, like a cosmic lattice extending in all directions. Under normal circumstances, if we were moving slowly or were stationary, this grid would appear straightforward. Looking ahead, we'd see the grid lines converging toward a vanishing point due to perspective, the same way railroad tracks appear to converge in the distance. But now we're not moving slowly. We're traveling at a substantial fraction of light speed. The aberration effect that's shifting the apparent positions of stars also distorts the appearance of this grid. Instead of seeing straight lines converging smoothly to a vanishing point, we see something much stranger. The grid appears to curve and bend around us. Lines that should be straight appear warped. The geometry of space itself seems twisted. If we were to pass close to an object, a planet or an asteroid, we'd see it appear to rotate as we flew by, even though it's not actually rotating at all. This is known as Terrell-Penrose rotation, named after the physicists who first described this effect mathematically. It's a direct consequence of the finite speed of light combined with our high velocity. Here's why it happens. When we look at an object, we're seeing light that left different parts of that object at different times. If we're moving very fast relative to the object, and the object has some size to it, the light from the far side of the object has to travel a greater distance to reach our eyes than the light from the near side. This creates a time delay. We're seeing the far side as it was slightly in the past compared to the near side. This time difference creates the illusion of rotation. An object passing by our spacecraft at high relative velocity would appear twisted, rotated, its shape distorted in peculiar ways. The faster we go, the more pronounced this effect becomes. The entire visual landscape around us takes on a surreal quality. with perspectives and proportions that would never occur at everyday speeds. Now, let's consider what's happening back on Earth as we accelerate away into space. We have a powerful telescope aboard our ship, one that can zoom in on our home planet despite the growing distance. What do we see when we point this telescope back at Earth? The planet appears to be moving in slow motion. If we could observe people walking on the surface, they would seem to move sluggishly, as if wading through molasses. Clocks would tick at a reduced rate. Waves crashing on shores would appear to break in dreamy slow motion. The entire planet seems to be operating at reduced speed. This is the Doppler effect, applied to light. You're probably familiar with the Doppler effect for sound. When an ambulance approaches you with its siren blaring, the pitch sounds higher than normal. As it passes and moves away, the pitch drops lower. This happens because the motion of the ambulance compresses the sound waves when it's approaching and stretches them out when it's receding. Light exhibits the same behavior. When a light source moves away from you, the light waves get stretched out. The wavelength increases, which for visible light means a shift toward the red end of the spectrum. This is called redshift. Along with this shift in color comes a reduction in the frequency of the light waves, which translates to a slowing down of any periodic processes we observe. From our accelerating spacecraft, Earth is receding at an ever-increasing rate. The light from Earth is redshifted. The clocks we observe tick slowly because we're receiving those clock ticks at a reduced frequency. We're watching events on Earth unfold at a reduced rate, not because time on Earth has actually slowed down, but because of the way the light from those events reaches us. The planet itself appears to take on a reddish hue as its light shifts toward longer wavelengths. If we could measure precisely, we'd find that all the spectral lines in the light from Earth have moved toward the red end of the spectrum, with the amount of shift depending on our velocity. Meanwhile, look forward again. The stars ahead of us show the opposite effect. We're moving toward them, catching up to their light. The light waves get compressed, shortened. The wavelength decreases, shifting toward the blue end of the spectrum. This is called blue shift. The stars ahead become not only brighter due to aberration, but also bluer in color. Any processes we could observe on planets ahead of us would appear to happen at an accelerated rate. Clocks would tick faster. Events would unfold in fast forward. These effects, the aberration, the Terrell-Penrose rotation, the Doppler shifting of light, they're all real phenomena that we could measure with instruments aboard our spacecraft. However, there's something important to understand about them. If we decided right now to stop accelerating, turn our ship around, and return to Earth, these effects would all reverse and disappear. When we got back to Earth, we'd find that the total elapsed time on our clocks matched the total elapsed time on Earth's clocks, accounting for the time it took us to make the journey. In other words, these are essentially optical effects. They're consequences of the finite speed of light and our motion relative to the light sources we're observing. They don't represent fundamental changes to the fabric of space and time itself. They're more like illusions created by the way light propagates and how we intercept it while in motion. But we've only just begun our journey. We've been accelerating for days now, and our velocity continues to climb. The instruments tell us we're now moving at a significant fraction of the speed of light. 50%, 60%, 70%. And as we push into these truly relativistic velocities, something changes. The effects we're about to encounter are no longer mere optical illusions. They're real, physical consequences of the structure of spacetime itself. We're entering the domain of Einstein's special relativity, and the universe is about to become very strange indeed. The first truly relativistic effect we need to discuss is time dilation, one of the most famous and mind-bending predictions of Einstein's theory. To understand time dilation, we need to think about the universe in a different way than we're used to. We typically think of space and time as separate things. Space is where things happen. Time is when things happen. But Einstein showed us that this separation is artificial. Space and time are not separate entities, but are instead woven together into a single four-dimensional fabric called spacetime. Imagine spacetime as a vast four-dimensional structure. Three of those dimensions are the familiar dimensions of space: length, width, and height. The fourth dimension is time. Every object in the universe, every particle, every person, every planet traces out a path through this four-dimensional spacetime. We call this path a world line. Even when you think you're sitting still, you're not truly stationary in spacetime. You're constantly moving through the time dimension, advancing from one moment to the next, progressing from your past toward your future. Your world line extends through spacetime, representing your entire existence from birth to death as a four-dimensional structure. Before our spacecraft launched, we were on Earth. Our world line through spacetime was aligned with Earth's world line. We were moving through time at the same rate as everything else on the planet, all advancing toward the future together, all keeping pace with one another through the time dimension. But when our spacecraft launched and began to accelerate, something fundamental changed. Our world line through spacetime began to diverge from Earth's world line. We started moving through space at high velocity, and this motion through space affects our motion through time. Here's the key insight of special relativity. There's a kind of trade-off between motion through space and motion through time. The faster you move through space, the slower you move through time. It's as if there's a speed limit for your total motion through spacetime. When you're sitting still in space, all of your motion through spacetime is directed through the time dimension. You age at the maximum rate. But when you start moving through space at high speed, some of that motion through spacetime gets redirected from the time dimension into the spatial dimensions. The result is that you age more slowly. This is time dilation. The faster you move through space relative to someone else, the slower your clock ticks compared to theirs. It's not that your clock malfunctions or that you perceive time passing differently. Your clock is working perfectly, and from your perspective, time passes normally. But when you compare your clock to the clock of someone who wasn't moving with you, you'll find that less time has elapsed for you. On our spacecraft, accelerating to relativistic speeds, time dilation is beginning to affect us. For every hour that passes on our ship, more than an hour is passing on Earth. The faster we go, the larger this discrepancy becomes. At 90% of light speed, our clocks run at about 44% of the rate of Earth clocks. At 99% of light speed, we're down to about 14%. At 99.9%, less than 5%. If we were to maintain this high velocity for what feels like a year to us, then turn around and return to Earth, we'd find that far more than a year had passed on our home planet. Our friends and family would have aged while we aged much less. We would have literally traveled into Earth's future. This isn't science fiction. This is established physics, confirmed by countless experiments. Particles accelerated to high speeds in particle accelerators live longer than they should because time dilation slows their internal decay processes. Atomic clocks flown on fast-moving aircraft tick at different rates than identical clocks left on the ground, with the difference matching special relativity's predictions to exquisite precision. Time dilation becomes more and more extreme as we approach the speed of light. If we could somehow reach 99.9999% of light speed, time dilation would be so severe that we could travel for what feels like mere minutes and return to Earth to find that centuries had passed. We could, in principle, journey to Earth's distant future, witnessing the world thousands of years from now while having aged only briefly ourselves. But there's a catch, of course. We can travel to the future, but we can't travel to the past. Time dilation only works in one direction. Once we've made our journey and returned to find Earth far in the future, there's no going back to our original time. We're now in that future, and it's our present. Time dilation has another strange consequence. Different observers, moving at different velocities, will disagree about whether two events happened at the same time. Events that appear simultaneous to one observer will not appear simultaneous to another observer moving at a different velocity. This is called the relativity of simultaneity, and it's one of the aspects of special relativity that most strongly contradicts our everyday intuition. Imagine two events occurring in space, one on Earth and one on a distant star. From Earth's perspective, these events happen at the same time. But from the perspective of our fast-moving spacecraft, the event on the distant star might happen before the event on Earth, or after it, depending on our direction and speed of travel. There's no absolute universal now that extends across the universe. Different observers have different definitions of simultaneous events, and all of these definitions are equally valid. This doesn't mean that causality is violated. An event can never affect another event in its past. The sequence of cause and effect is preserved for all observers, but the timing of events that don't causally affect each other can be different for different observers, and this is a fundamental feature of how spacetime works. Now, let's turn to another major consequence of special relativity: length contraction. This effect is intimately related to time dilation, two sides of the same relativistic coin. As we've accelerated our spacecraft to high speed, something has happened to the structure of space itself from our perspective. The universe has contracted in the direction of our motion. Distances between objects that lie along our direction of travel have shortened. This isn't an optical illusion or a trick of perception. From the reference frame of our spacecraft, the physical distance from our ship to any destination ahead of us is genuinely shorter than the distance as measured by someone at rest relative to those destinations. At 90% of light speed, distances along our direction of motion are contracted to about 44% of their rest length. At 99% of light speed, distances shrink to about 14%. At 99.9%, we're down to less than 5% of the original distance. Think about what this means for interstellar travel. The nearest star system to Earth, Alpha Centauri, is about 4.3 light-years away as measured from Earth's reference frame. If we were traveling to Alpha Centauri at 99.9% of light speed, length contraction would shrink that distance from our perspective to less than 2/10 of a light-year. From our point of view aboard the spacecraft, the journey wouldn't take 4.3 years. It would take much less time, because the distance we need to travel is much shorter due to length contraction. Combined with time dilation, this creates a remarkable possibility. Despite the cosmic speed limit imposed by the speed of light, we could, in principle, travel enormous distances across the galaxy in what would feel like a very short time to us aboard the spacecraft. We could travel hundreds or even thousands of light years in what feels like months or years of shipboard time, getting arbitrarily close to light speed to make the journey shorter and shorter from our perspective. There's a common misconception that the speed of light makes interstellar travel impossible or impractical because it would take too long. From Earth's perspective, this is true. A journey to a star 1,000 light-years away at near light speed would take roughly 1,000 years of Earth time. But from the perspective of the travelers, length contraction and time dilation compress that journey dramatically. At 99.99999% of light speed, the travelers would experience only a tiny fraction of that time. The journey would feel nearly instantaneous. Of course, there's a catch. When those travelers returned to Earth, they'd find that thousands of years had indeed passed. Everyone they knew would be long dead. Civilizations would have risen and fallen. They could explore distant reaches of the galaxy, but only at the cost of leaving their own time behind forever. Length contraction, like time dilation, becomes more extreme as we approach light speed. In principle, if we could reach exactly the speed of light, which we'll see shortly is impossible, distances in the direction of motion would contract to zero. The entire universe in front of us would become infinitely compressed, flattened to zero thickness. We could theoretically traverse the entire observable universe instantly from our perspective. But here's where things get visually complicated. You might expect that with length contraction, objects would appear squished and compressed in the direction of motion. If we passed by a planet at 99% of light speed, shouldn't the planet look like a flattened pancake? Surprisingly, no. This is where the Terrell-Penrose rotation effect we discussed earlier comes back into play. Length contraction is a real physical phenomenon, but the visual appearance of objects moving at relativistic speeds is affected by the finite speed of light and the time it takes for light from different parts of an object to reach our eyes. Consider a planet that we're approaching at high speed. Yes, due to length contraction, the planet is physically compressed in the direction of our motion. But remember, we see different parts of the planet as they were at different times. The light from the far side of the planet has traveled a greater distance to reach us than light from the near side. We're seeing the far side, as it was in the past. Even though the planet is contracted, we receive the image of its rear portion with a time delay. This delay exactly compensates for the length contraction, making the planet appear rotated rather than squished. Instead of looking like a flattened disk, the planet looks like a sphere that's been turned, showing us a view of its far side that we wouldn't normally be able to see. The same applies to any object we observe at relativistic speeds. A person standing to the side of our path would appear rotated, not compressed. A building would seem twisted. The visual effect is one of distortion and rotation rather than simple squashing. This is one of the most counterintuitive aspects of relativistic travel. Length contraction is real and measurable, affecting the actual distances and dimensions we experience, but it doesn't produce the visual appearance you might naively expect. The interplay between length contraction, the finite speed of light, and our high velocity creates visual effects that are more subtle and complex. As we continue to accelerate, both time dilation and length contraction grow more and more extreme. Our field of view continues to change. The aberration effect intensifies further. More and more starlight concentrates in the forward direction, while the rearward view becomes a void of near-total darkness. The stars ahead cluster tighter and tighter toward a shrinking region of sky. The intensity of light from that direction grows brighter and brighter, blue-shifted to higher and higher energies. If we're not careful, the radiation from this concentrated starlight could actually become dangerous, shifting from visible light into ultraviolet, then X-rays, then gamma rays, as the Doppler effect compounds. Behind us, the darkness is nearly complete. Any remaining starlight from that direction is so redshifted that it's dropping out of the visible spectrum, shifting into infrared and beyond. The universe behind our spacecraft has effectively vanished from view. Our instruments continue to show our velocity climbing. 98% of light speed, 99%, 99.9%. The question naturally arises, what happens if we keep accelerating? Will we eventually reach the speed of light? And if so, what would we see at that ultimate velocity? This question cuts to the heart of special relativity. The answer is perhaps the most fundamental insight of Einstein's theory. No matter how long we accelerate, no matter how much energy we pour into our engines, we will never reach the speed of light. The speed of light is not just another speed. It's a fundamental constant of the universe, the same for all observers regardless of their motion. This is the central postulate of special relativity, and it leads to all the other strange effects we've been discussing. Here's the profound implication. Light always moves at the speed of light relative to you, no matter how fast you're moving. If you're stationary and you shine a flashlight, the light beam travels away from you at light speed. If you're moving at 99% of light speed and you shine a flashlight forward, that light beam still travels away from you at the full speed of light, not at 1% of light speed, as you might expect. This seems impossible. How can light always have the same speed relative to every observer? The answer is that space and time are flexible. They warp and adjust themselves so that light speed remains constant. This is why time dilation and length contraction occur. They're the universe's way of ensuring that light speed is the same for everyone. Because of this, there's no reference frame in which light is stationary. You can never catch up to a light beam. No matter how fast you go, light always outraces you at exactly the speed of light. From Earth's perspective, our spacecraft can get arbitrarily close to light speed. We could reach 99.9999999% of light speed or even closer, but we can never quite get there. As we approach light speed, several things happen that prevent us from ever reaching it. First, our mass effectively increases. The energy we pump into our engines doesn't just increase our velocity, it also increases our kinetic energy, which from the perspective of special relativity is equivalent to increasing our mass. The closer we get to light speed, the more massive we become, and the more energy is required to accelerate us further. At exactly light speed, our mass would become infinite, requiring infinite energy to maintain that velocity. Second, time dilation means that from our perspective aboard the spacecraft, we're not approaching light speed at all. Remember, we can't feel our velocity. From our reference frame, we're always at rest. Light always travels past us at light speed, no matter how fast we're going relative to Earth. If we accelerate constantly for what feels like a year aboard our ship, from Earth's perspective, we might be traveling at 99.999% of light speed. But aboard the ship, if we turn on a flashlight and point it forward, we still see the light beam traveling away from us at full light speed. From our perspective, we're stationary, and light is still escaping us at the same rate it always has. This creates a strange situation. We can accelerate forever, for years and years of shipboard time, and our velocity relative to Earth will keep climbing closer and closer to light speed. But from our perspective, nothing fundamentally changes. We never feel like we're approaching a limit. Light continues to escape us at light speed, just as it did when we started our journey. What would happen if we just kept accelerating forever? Our field of view would continue to compress forward. The concentration of blue-shifted high-energy radiation ahead of us would grow brighter and brighter, forming an ever-shrinking spot of unbelievably intense light, surrounded by complete blackness. Eventually, essentially all the light from the entire observable universe would be concentrated in a tiny bright region directly ahead, while everywhere else would be pitch black. From our perspective, due to length contraction, the universe would become thinner and thinner in the direction of motion, compressed into an ever narrower band that we're slicing through. The entire cosmos would be flattened into what would feel like a thin sheet that we're traversing almost instantaneously. Meanwhile, on Earth, observers would see us approaching light speed asymptotically, getting closer and closer, but never quite reaching it. Time dilation would be so extreme that they'd see our clocks ticking incredibly slowly. To them, we'd appear to be frozen in time, barely moving forward in time at all as we raced through space at just barely below light speed. So in conclusion, at least as far as conventional physics goes, we can never see what the universe looks like at exactly light speed because we can never reach that speed. We can only approach it, getting closer and closer, seeing the effects become more and more extreme, but never quite getting to the limit itself. Light speed is a barrier, a cosmic speed limit that cannot be exceeded or even reached by any object with mass. But this raises an interesting question. Special relativity tells us that nothing can move through space faster than light. But what about space itself? What if we could find a way to move space rather than moving through it? This is where general relativity, Einstein's theory of gravity and curved spacetime, opens up some fascinating possibilities. General relativity teaches us that spacetime is not a fixed, rigid stage on which events play out. Instead, spacetime is dynamic. It can bend, curve, stretch, and compress in response to mass and energy. We see this most dramatically in the phenomenon of gravity. What we experience as gravitational attraction is actually the curvature of spacetime around massive objects. Earth curves the spacetime around it, and we follow the curved paths through that spacetime, which we perceive as falling toward Earth. But curvature isn't the only thing spacetime can do. Spacetime can also expand or contract. In fact, the entire universe is doing this right now. The space between distant galaxies is expanding, carrying those galaxies apart from one another. This expansion can happen at any rate. In the early universe, during a period called cosmic inflation, space expanded far faster than the speed of light, inflating the universe by an enormous factor in a fraction of a second. Importantly, this expansion doesn't violate relativity because the galaxies aren't moving through space faster than light. The space itself is expanding, carrying the galaxies along with it. The restriction on faster-than-light travel applies to motion through space, not to the expansion or contraction of space itself. This observation has led physicists to speculate about a hypothetical propulsion system called a warp drive. The idea is to create a bubble of space-time around a spacecraft that propels the bubble, and the ship inside it, forward by contracting space in front of the ship and expanding space behind it. The ship itself wouldn't move through space. It would remain stationary inside its bubble. But the bubble would move, surfing on a wave of expanding and contracting spacetime, and this wave could potentially move faster than light because there's no law of physics preventing spacetime itself from moving that fast. This concept was formalized mathematically by physicist Miguel Alcubierre in 1994. The Alcubierre drive, as it's called, is a solution to Einstein's equations of general relativity that describes exactly this kind of warp bubble. On paper, it works. The mathematics is consistent with general relativity, but there are enormous, probably insurmountable practical problems. The first problem is energy. Creating an Alcubierre warp bubble would require warping spacetime dramatically, and this warping requires vast amounts of energy. Initial calculations suggested you'd need more energy than exists in the entire observable universe. Later, refinements brought this down somewhat, but it's still an almost unimaginably large amount of energy, far beyond anything we could conceivably generate. The second problem is even more fundamental. The type of energy required appears to be negative energy, or equivalently, negative mass. In general relativity, mass and energy curve spacetime in specific ways. Positive mass and energy create the kind of curvature we associate with gravity, an attractive force. To create the opposite kind of curvature needed for a warp drive, you'd need negative mass or negative energy. Does such a thing exist? In quantum physics, there are phenomena like the Casimir effect that can be interpreted as producing tiny amounts of negative energy under very specific circumstances. But whether this could be scaled up to the amounts needed for a warp drive, and whether negative mass exists at all as a stable form of matter, is unknown. Most physicists are skeptical. There are also causality problems. If you could travel faster than light, even using a warp drive, you could potentially create situations that violate causality, allowing effects to precede their causes. This would open the door to time travel paradoxes. It's possible that the laws of physics inherently prevent any form of faster-than-light travel, including warp drives, specifically to avoid these paradoxes. Despite these problems, it's fun to speculate. If we somehow could build a working warp drive, what would we see? The view from outside the warp bubble would be bizarre. As the bubble approached at faster-than-light speeds, it would seem to appear out of nowhere. The curvature of spacetime around the bubble would bend light rays in complex ways, creating a kind of moving gravitational lens effect. Light from behind the bubble would be focused and distorted as it passed around the warped region. To an outside observer, the bubble might appear to split into two images, one moving forward and one moving backward, as light rays take different paths around the curvature. After the bubble passed, there would be a similar effect in reverse. The observer would see distorted, lensed images of the bubble even after it had gone by, as light that took longer paths around the curved region finally arrived. From inside the bubble, the view would be stranger still. Looking forward, you'd see the stars dramatically concentrated and blue-shifted, even more so than in conventional near-light-speed travel. The intensity of radiation from ahead would be enormous. A blinding concentration of light blue-shifted into gamma rays. Looking behind, you'd see not just darkness, but a complete absence of information from a large region of space. There would be a cone-shaped region of the universe from which no light could reach you at all. Because the warp bubble is moving faster than light, any light emitted from within this cone can never catch up to the bubble. It's moving away from those regions of space faster than their light can travel. This creates a permanently invisible zone behind the ship. Events happening in that zone would be forever unobservable to you as long as you maintained your faster-than-light velocity. You'd be outrunning the information itself, leaving a trail of causally disconnected spacetime in your wake. When you decelerated and stopped, this zone would catch up. Light from those previously invisible regions would eventually reach you, and you'd see everything that happened during your journey all at once, compressed in time. The universe outside the bubble would also appear heavily distorted by the extreme curvature of the warp field. Stars would appear in the wrong positions, their light bent and refracted by the warped spacetime. The entire view would shimmer and shift as you moved, the lensing effects changing constantly. Inside the bubble itself, however, spacetime would be flat and normal. You wouldn't feel any acceleration. You wouldn't feel any motion at all. You'd be in a small, isolated pocket of normal spacetime, surfing on a wave of distorted spacetime around you. It's a fascinating concept. Even if it remains purely theoretical, the warp drive represents the ultimate expression of the principle that while you can't move through spacetime faster than light, you might be able to move spacetime itself. But setting aside speculative technologies like warp drives, let's return to what we know is possible, at least in principle: conventional travel, approaching light speed. Our velocity reads 99.999% of the speed of light. We've been traveling for what feels like several months aboard the ship, though back on Earth, years have passed. Perhaps decades. The relativistic effects are now so extreme that the universe has transformed into something almost unrecognizable. Look ahead through the forward viewport. What was once a sky full of stars distributed across a hemisphere of view has now collapsed into a tiny, brilliant circle of light directly in front of us. This spot is blindingly intense, pulsing with energy that has been blue-shifted far beyond the visible spectrum. If we could see with instruments sensitive to X-rays and gamma rays, we'd detect that most of the radiation concentrated in this forward spot is now in those high-energy bands. Every star, every galaxy that lies ahead of us has been compressed by aberration into this shrinking cone of view. The Doppler effect has shifted their light so far toward the blue end of the spectrum that what were once cool red stars now blaze with the intensity of blue giants. White stars have shifted into ultraviolet, and stars that were already blue are now emitting primarily in X-rays. The concentration of energy is staggering. If our ship weren't equipped with some kind of shielding, we'd be bathed in lethal radiation. This is one of the practical hazards of relativistic travel that science fiction sometimes overlooks. At these speeds, even the cosmic microwave background radiation, that faint afterglow of the Big Bang that permeates all of space, gets blue-shifted into dangerous territory. The gentle 3-degree Kelvin microwave radiation becomes searing gamma rays pounding our ship from ahead. Behind us, there's nothing. Absolute darkness. Any star or galaxy in the rearward hemisphere has been so severely redshifted that its light has dropped completely out of any detectable range. The photons have been stretched to wavelengths meters long, kilometers long, their energy diluted to near nothingness. For all practical purposes, the universe behind us has ceased to exist as far as our instruments can detect. To the sides, in the perpendicular directions, we'd see a strange ring of distorted starlight, forming a circular band around our field of view. This ring represents the original equatorial plane of the sky, compressed by aberration into a narrow belt. Stars in this ring would appear highly distorted, their shapes stretched and warped by the extreme Terrell-Penrose rotation effect. Our entire journey to this point has taken us deeper and deeper into relativistic territory. But we've hit a kind of asymptotic approach. We can keep accelerating, keep pumping energy into our velocity, but the returns diminish. Going from 99% to 99.9% of light speed required far more energy than going from 90% to 99%. Going from 99.9% to 99.99% would require even more energy still. This is because of the way relativistic mass works. As we approach light speed, the energy we add to our velocity doesn't just make us go faster, it makes us more massive from the perspective of observers in other reference frames. This growing effective mass makes it harder and harder to accelerate us further. Eventually, we'd need infinite energy to actually reach light speed, which is why it's impossible. From our perspective aboard the ship, though, something different is happening. We don't feel heavier. We feel completely normal. Our clocks tick at their normal rate. Our bodies age normally. If we look at a clock on the wall, it's ticking once per second, just as it always has. But if we could somehow observe a clock on Earth, zooming in with our impossible telescope despite the vast distance, we'd see that clock ticking incredibly slowly. Fractions of a second on Earth's clock pass, while minutes tick by on ours. Time dilation has become so extreme that we're nearly decoupled from Earth's time stream entirely. And if we measured the distance to our destination, some star system dozens of light years away from Earth, we'd find that due to length contraction, that distance has shrunk to perhaps a few light months, or light weeks, or even less. the faster we go, the shorter the journey appears to us. This creates one of the most fascinating aspects of relativistic travel. From Earth's perspective, our journey to a star 20 light-years away at 99.999% of light speed would take just slightly more than 20 years. The people on Earth would watch us crawl across the cosmos at just barely below light speed, taking decades to reach our destination. But from our perspective, that same journey might feel like it takes only a few weeks or months. The combination of length contraction shortening the distance and our clocks running normally from our point of view means the journey is genuinely quick for us. We experience far less subjective time than the Earth observers do. This isn't an illusion. When we arrive at our destination, our clocks will have recorded less elapsed time than Earth's clocks. We will have aged less. If we turned around and came back, we'd return to Earth decades in the future, having aged only months or years ourselves. This is real time travel, into the future only. It's been confirmed countless times with particle physics experiments, with precise atomic clocks on aircraft and satellites, with observations of cosmic ray particles. Time dilation and length contraction are not theoretical speculations. They're measured, verified facts about how our universe works. Now, let's address the question that's been hovering over this entire journey. What would happen if we actually reached light speed? What would the universe look like from the perspective of a photon, traveling at exactly the speed of light? The answer is both simple and deeply strange. The question itself doesn't make sense. There is no reference frame traveling at light speed. There is no perspective of a photon. In special relativity, reference frames are defined for objects moving at less than light speed. The equations that transform between different reference frames, called the Lorentz transformations, break down at exactly light speed. Time dilation becomes infinite. Length contraction reduces distances to zero. The mathematics produces infinities and undefined values. What does this mean physically? One way to interpret it is that from the perspective of a photon, if such a perspective could exist, no time passes at all. A photon, emitted from a distant galaxy billions of light years away and absorbed by your eye, when you look at that galaxy, experiences zero elapsed time between emission and absorption. From its own perspective, the journey is instantaneous. Similarly, distances along the direction of travel would be contracted to zero. The entire universe along the photon's path would be compressed to a single point. The photon would be everywhere along its trajectory simultaneously. But again, this isn't really a valid way to think about it because there is no reference frame for the photon. The photon doesn't experience anything. It doesn't have a perspective. It simply travels at light speed. And that's a fundamental difference from objects traveling at any slower speed. For us aboard our spacecraft, no matter how long we accelerate, we will never reach this state. We will always be in a valid reference frame, always experiencing time passing normally, always seeing light travel past us at light speed. We can get arbitrarily close to light speed as measured by Earth, but we can never reach it ourselves. If we accelerated continuously for years and years of shipboard time, our velocity relative to Earth would approach light speed ever more closely. 99.9999%. 99.99999%. We could add as many nines as we want, but there would always be a tiny difference, a minuscule gap between our speed and the speed of light itself. And throughout this entire time, if we turned on a flashlight and pointed it forward, we would still see the light beam moving away from us at exactly the speed of light. Not at a reduced speed, not at a crawl. At full light speed, 299,792,458 meters per second, the same speed it's always been. This is the central mystery and the central insight of special relativity. Light speed is absolute. It's the same for every observer, no matter their motion. This seems impossible, seems to violate common sense. But it's how the universe works. Space and time themselves are flexible, warping and adjusting to ensure that light speed remains constant for everyone. So, at our maximum velocity, as close to light speed as we can get, the universe would be compressed ahead of us into a brilliant point of high-energy radiation. Behind us, would be darkness. We would be threading through a universe that, from our perspective, is flattened into an impossibly thin sheet. We could traverse vast cosmic distances in subjective moments, but we could never quite reach the ultimate limit. This brings us to our final speculation: the warp drive. If we can't move through space faster than light, what if we could move space itself? General relativity, Einstein's theory of gravity and curved spacetime, tells us that spacetime is not a fixed backdrop. It's a dynamic entity that responds to mass and energy. Massive objects like stars and planets curve the spacetime around them, and this curvature is what we experience as gravity. But curvature isn't the only thing spacetime can do. The fabric of spacetime can also expand or contract. We know this happens on cosmological scales. The space between distant galaxies is expanding right now, carrying those galaxies apart from one another. This expansion can proceed at any rate, including faster than light. Because the galaxies aren't moving through space, the space between them is growing. In the very early universe, during the first tiny fraction of a second after the Big Bang, space underwent a period of exponential expansion called cosmic inflation. In an incomprehensibly brief instant, space expanded by a factor of at least 10 to the power of 26, possibly much more. This expansion was far, far faster than light speed. Yet it didn't violate relativity because nothing was moving through space faster than light. Space itself was expanding. This observation led some physicists to wonder, could we harness this kind of space-time manipulation for propulsion? Could we create a region of space around a spacecraft that contracts in front of the ship and expands behind it, propelling the ship forward by riding a wave of space-time? This concept was formalized by physicist Miguel Alcubierre in 1994. He found a solution to Einstein's field equations that describes exactly this scenario. The Alcubierre metric, as it's called, represents a bubble of flat spacetime containing the spacecraft, surrounded by a region of severely warped spacetime that moves the bubble forward. The view at the speed of light, or rather infinitely close to it, is a universe compressed into a brilliant point ahead, surrounded by darkness. It's a cosmos reduced to a thin sheet we traverse in instants. It's a reality where we age slowly while the worlds we left behind rush forward in time. It's a universe far stranger than we imagined, yet precisely as strange as the mathematics predicts. And in that correspondence between theory and reality, between abstract equations and concrete observations, we find one of the deepest truths about the cosmos. It is comprehensible. Weird, yes. Counterintuitive, absolutely. But ultimately understandable through reason and evidence. That's the real journey we've taken. Not just a journey through space toward light speed, but a journey of understanding. From familiar intuitions to profound insights about the nature of reality itself. And that journey, unlike relativistic space travel, is one we can all take, right here and now. By studying the universe and learning its secrets, the cosmos awaits, strange and beautiful, and endlessly fascinating. All we have to do is look.